Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. In this lecture, we're going to discuss an interesting problem, and that is we want to derive the operator that allows you to get the momentum from a wave function, right? So how do you do this, and what are the steps involved? By way of review, right, there are many operators in quantum mechanics. We've focused pretty much solely on the Hamiltonian H, which operates on the wave function psi to give you the energy eigenvalue E for the quantum state that's described by that wave function psi. So that's the energy operator. It's called the Hamiltonian, and it's abbreviated capital H. In the last lecture, we talked about a momentum operator. Momentum operator is some quantity which operates on the wave function psi and gives you the position of the wave function of the particle x back again. And the operator x with a hat over it, subscripted by OP, right? That operator can be used to define an expectation value of position by sandwiching that operator between psi star and the wave function psi and integrating over the relevant range of x. And we make use of this definition here for the eigenvalue problem, right? And it allows us to replace x operator times psi by the position coordinate x times the wave function psi, and that gives us this equation, which we evaluated for the special case of a particle in the second quantum state of an infinite square well. That was the way we wrapped up the last lecture, right? In this lecture, we want to ask the question, what is the momentum operator? And the reason we would need to know that is because we like to ask the question very often, what is the expectation value of the momentum of a quantum particle in a particular system, right? And so we have to work a little bit to get this expression for the momentum operator. So let me just say that we define the expectation value of the momentum in a rather obvious way. It's the mass of the particle times the expectation value of the velocity. The expectation value of the velocity is the time derivative of the expectation value of the position, and the value of the expectation value of the position, of course, is defined by this equation up here. So if we want to calculate the expectation value of momentum, we have to take the time derivative of this integral, psi star x psi dx. And what I'm going to do here is I'm just going to write the answer down, and then in the next few slides I'll show you how that answer is obtained. So the answer is that the momentum operator turns out to be minus I h bar times the derivative with respect to x. And that operator placed between psi star and psi and integrated over the relevant range of positions then gives you the expectation value for the momentum p. So this is the result that you need to remember. The calculation is performed in one dimension, the x dimension here, but this is the result that you need to answer all the questions that might come up about expectation values for momentum. Now, how do you get that? Well, to obtain that result requires about 3 pages of algebra. And I'm not going to go through all the steps here. You're welcome to look at it. It's all provided in all its gory detail. It involves simplifying integrals. There's a lot of terms that eventually cancel out, so I've tried to show what terms cancel by using different colors of lines. And at the end of the day, what you find is that this expectation value for momentum is going to be given by this minus I h bar partial with respect to x, okay? So please, if you're interested in the algebra, please take a look at that, and you can track through it. What we're going to focus on in the lecture is mostly what are expectation values for momentum of particles in different situations, right? So, for example, we can ask what is the expectation value for the momentum and the square of the momentum for an electron in the n equals 2 state of the infinite square well. So this mirrors, precisely mirrors the calculations we did for the expectation value of position and the expectation value of x squared for a particle in an infinite square well. So first thing we need to do to answer part A, we're going to calculate the expectation value of the momentum. We have to write down the appropriate wave function for a particle in the n equals 2 state. And then we have to evaluate the expectation value based on this definition of the momentum operator. And this definition of the momentum operator says you take the first derivative of the wave function with respect to x, multiply it by minus I h bar, then integrate the result that you obtained after you multiply by psi star. You have to integrate over all values of x in this case. So again, the arithmetic, I think, is pretty simple. When you take the derivative of sine, you're going to end up with a cosine function. So you're going to have a cosine times a sine. The reason this sine comes in is because the wave function is real. So psi star of a real function is just sine again, right? So that there's nothing strange there. You have to recognize that the limits of the integral have to be adjusted to match the problem. So you're going to be integrating from minus L by 2 to plus L by 2. That's simply because the wave function psi is 0 once x is greater than L by 2 or once x is less than minus L by 2. So when you try to extend this integral from minus infinity to infinity, you're going to naturally get 0 because these wave functions are going to vanish outside the range of the square well. And again, this integral is easy to evaluate because it involves the product of an odd function times an even function. And anytime you multiply an odd function times an even function and try to integrate it over symmetric range of values of x, you're going to get, by definition, equal to 0. And so what this means is, that if you put a particle in the n equals 2 quantum state of an infinite square well, and you did measurements to measure its momentum, and if you average those measurements, let's say you have to perform a few hundred measurements to get a good average value, what you would find is that the momentum of the particle on average is equal to 0. Now, that should not be too terribly surprising because this quantum state is actually a standing wave, right? And we went through a considerable effort in the early part of the course to try to convince you that a standing wave is equivalent to a wave moving to the left plus a wave moving to the right. And so if you have a wave, two waves moving in the opposite direction and each wave carries a momentum p, right, the net momentum for that situation is going to be precisely equal to 0. So that's what the interpretation of this calculation is. And as often in quantum mechanics, the calculation is one thing, understanding what the result means is another separate item that requires some physical insight. The second part of this problem is to evaluate the expectation value of the square of the momentum. And again, it's a straightforward calculation. It just requires you to realize that you now have to put the momentum operator into this expectation integral twice, right? So you got p squared here, you got to put p times p. These are the operators. These operators operate on this wave function, and after you perform the numerical calculation of this operator operating on this wave function, and then you have to do it again, right? You have to basically take two derivatives here. So let's see. The wave function is sine. It's a sine function, so you have to put that into the equation. You have to take the derivative with respect to the sine. When you do that, you get a cosine function. Notice that we've again adjusted the limits of the integral from minus L by 2 to plus L by 2. That's important because the square well only has a finite width, L, right? And that is reflected by adjusting the limits of the integral. After you take the first derivative to get the cosine, then you have to take a second derivative of the cosine to get the wave function back again. That's the sine, right? Every time you take a derivative, you get a factor of 2 pi over L that comes out. And so you've got a 2 pi over L quantity squared that multiplies everything. The minus I h bar that multiplies each other, that turns into this h bar squared here. And you're left with this integral from minus L by 2 to plus L by 2 of sine squared. That can be evaluated in a pretty straightforward way. And what you find is, at the end of the day, that the expectation value of the momentum squared is 4 pi squared h bar squared over L squared. So there are two issues, right? There are two issues that I want to emphasize. First is, are these units correct, right? So I work out the units. H bar has units of joules seconds. The length L has units of meters. So we want to make sure that joules seconds quantity squared divided by meters squared is in fact equal to a momentum squared. And so I work that out and try to convince you that the units are okay. And then the second thing I want to emphasize is a sanity check, right? How do you understand this result? Well, the way I understand it is, right, the expectation value for the energy of a particle in this square well is going to be the expectation value for the kinetic energy plus the expectation value for the potential energy in the square well. The expectation value for the kinetic energy is just the expectation value of p squared for the n equals 2 quantum state divided by twice the mass of the particle, plus the expectation value of the interaction potential. For the square well that we're dealing with, this interaction potential energy is equal to 0 inside the well, so we're left with this expression for the expectation value for the energy. You can rewrite this in a slightly different form, and that's what I do in this line. I just massage the final result into a form which I can then compare to the n equals 2 eigenvalue that we solved a few lectures back for the infinite square well. So if you recall, we had an expression for the eigenvalue n equals 2. It's equal to n squared h bar squared over 8 ml squared. When you simplify that and you find out, you get the exact same result that you got by evaluating the expectation value of kinetic energy, expectation value of potential energy. So the point is, the calculation makes sense, and this tries to give you some insight into why you would want to calculate the expectation value of p squared, right? Turns out that value comes in to an energy, kinetic energy calculation. And so if you want to know what the average or the expectation value for the kinetic energy is of a particle trapped in an infinite square well, one way to get that is to evaluate p squared over 2m, like I've done here. Okay? So that gives you an example of how these momentum operators are used in quantum mechanics. And it's important for you to understand that, because momentum is an important quantity that we try to keep track of. I'd like to point out that not all wave functions are eigenfunctions of an operator. So just because we've cooked up some operator that allows us to calculate an expectation value of a quantity, that does not mean that that operator when operated on by, when it operates on a wave function, satisfies an eigenvalue problem. And so I try to make that case here, right? So for instance, if you tried to calculate the momentum of this psi2 wave function for a particle in an infinite square well by trying to solve an eigenvalue problem like this, it wouldn't work, right? Because when you take the derivative of sine, you get a cosine. And so, you know, if you try to set this up as an eigenvalue problem, you'd find that the momentum operator times the wave function equals something times another function, and this function doesn't match this one, and because these two guys don't match, right, this is not an eigenvalue problem. So that just simply means that this wave function is not an eigenfunction of the momentum operator, right? And it leads to the somewhat contradictory conclusion that even though you can use this wave function to calculate the energy eigenfunctions for a particle in a square well, right? And you can get the energy eigenvalues out very nicely. We've already shown that in a prior lecture. It's not possible to get a definite value for the momentum in a measurement, right? Because this eigenvalue problem is not satisfied. So that begs the question then, okay, if sine of 2 pi, or sine of x over L is not an eigenfunction of momentum, what is an eigenfunction of momentum? And so what I do is I just work that out here. I try to show you that in principle, it's possible to calculate these things. I set up the eigenvalue problem here, and I'm going to try to derive an expression for psi that satisfies this particular differential equation. So what is the value of psi that satisfies this equation? Well, I just take the derivative of psi with respect to x, divide through by psi of x, and I move dx to the other side of the equation, and I end up with a result that says the change in psi with respect to x divided by the wave function psi at that point x is equal to a bunch of numbers times dx. And I hope you all recognize right away that this differential equation gives you a natural logarithm solution. It says that the natural logarithm of the wave function is equal to I momentum over h bar times x plus some constant c, and that means that you can rewrite the wave function in terms of a constant e to the c. This is some arbitrary constant that we just call a, times this e to the I p over h bar times x, which we abbreviate as e to the I kx, right? So p over h bar we represent by k. That's the wave vector of the particle. So it turns out that the free particle state, right, you should hopefully recognize that this e to the I kx is the wave function for a free particle. That free particle wave function is in fact an eigenvalue, is an eigenfunction for the momentum operator, right? So that answers the question, what is the eigenvalue, what is the eigenfunction of the momentum operator? The answer to that question, simple answer to that question is free particle wave function, okay? So I just turned the problem around again, right? You have to do these things to build up some confidence. I say prove that that wave function is in fact an eigenfunction of momentum. And the arithmetic here is pretty straightforward because you're just taking the derivative of an exponential function. Anytime you take the derivative of an exponential function, you get the function back again. Of course, you got to multiply by the derivative of the argument. And so what you find is that that in fact you can, using this free particle wave function, e to the I kx, you can satisfy an eigenvalue problem, and the eigenvalue turns out to be h bar k, right? So you get the wave function back again, what multiplies the wave function is h bar k, and so then you identify h bar k is the momentum of the particle, which is something that we've already done many times in the process of this course. The third thing, third example that we'd like to go through real quick is, let's calculate the expectation value of the momentum squared for a free particle. What answer do we get when we work that problem out? And again, this is more an example to reinforce the concept of expectation values and how you calculate them. So we need to write down the wave function of the free particle. That's the a times e to the ikx. We have to use that wave function in the expression for the expectation value of the momentum squared. That means that we have to put in the momentum operator twice. It also means that psi star now is going to involve e to the minus ikx, right? So if psi is equal to a e to the ikx, then clearly psi star is equal to a e to the minus ikx. So that also has to be put into the problem. I just focus on the numerator, right? And I work through the arithmetic. It's pretty straightforward. What you find is that the numerator in that prior expression is just h bar k quantity squared times this integral from minus infinity to infinity of psi star times psi, right? When you put that back into the expression for the momentum expectation value of momentum squared, you can see that the integral of psi star psi from minus infinity to infinity cancels. That gives you the expectation value for the momentum squared of a free particle. You can then use that to calculate the expectation value for the energy of a free particle, and it's just equal to h bar squared k squared over 2m, where m is the mass of that particle. So this is an important result, and we're going to keep coming back to it over and over again, right? We're going to use this to whenever we treat a particle as free, we're going to use this as the definition of the energy E of that particle. So that's why this particular result is important. In the appendix, I try to answer the question, what happens if you know psi of x and you want to find an eigenfunction of momentum, which we call phi of k, right? Turns out this is an interesting question, and I sketch out the solution to it here. This is sort of a precursor to a more elaborate discussion that we're going to hold on this particular problem in another week. So if you just read the appendix quickly, I hope you pick up the words and the ideas, because we're going to come back and we're going to work through the arithmetic on this and show in detail how, if you know the wave function in position, how you can get the eigenfunction of momentum in from that. So that's what this appendix is about. So I think that's the important point of this lecture, and I think the next two lectures we're going to investigate these free particle wave functions as they interact with potentials, potential barriers, potential steps, and we're going to try to understand how these free particles are scattered in the process of this interaction. So that's the topic of the next two lectures. We'll see you when you get a chance to look at those next.